Hello everyone, welcome to YouTube channel Energy-Exergy Theory Applications. I am Professor Tatiana Morozyuk and I am the author of this YouTube channel. Today we are with the topic exergy. All lectures have a very dynamic style of presentation. Definitely some of you would like to learn more, particularly about exergy. We will be happy to answer your questions and provide with an extended information. Our contact email you can find in the description of each video. Please support our work with a like to this video, subscribe the channel and share the link with your colleagues. Lecture 3 in the topic exergy will be dedicated to physical exergy. Let us repeat. Physical exergy is the maximum theoretical work that can be obtained if system is brought to the equilibrium from the given state to the so-called restricted thermodynamic environment or restricted dead state. And we already mentioned that restricted dead state associated with the fact that chemical properties of the system and the thermodynamic environment will be the same and chemical properties should be defined. If we will not now discuss chemical properties and we will only refer to the temperature and pressure of the system and temperature and pressure of the thermodynamic environment, restricted thermodynamic environment, then the situation will be the following. The higher temperature, so the more far we are from the temperature of the thermodynamic environment, the higher will be the exergy. And the same can be applied for low temperature processes. The low temperature than the environment, the higher the exergy. And as before, I asked GPT to produce a visualization of physical exergy. This is very interesting, and this figure colorful figure I got from ChatGPT, and we can see that it is like an expansion machine, started with the higher temperature and pressure, so higher exergy, and slowly move it to the direction to decrease the exergy to the status of zero of restricted thermodynamic environment. So as you can see, our discussions and visualizations that can be produced fully correspond to each other. It means that there is only this model of physical exergy, how to understand the physical exergy of the system and of the material stream. And here exactly we will discuss that there are different equations that exergy should be calculated for the system and for the material stream. System for us, according to thermodynamic definition, it is closed system, and material stream for us associated with open thermodynamic system when stream of the matter can cross the boundary of the system from system to surrounding, and for us surrounding it is thermodynamic environment. And equation for the physical exergy associated with closed system, it is the difference in internal energy between internal energy of system and thermodynamic environment, volume of the system, and also multiply to the pressure of the thermodynamic environment, and the term temperature of the thermodynamic environment, and the difference in entropy between system and environment. For the open system, equation will be a little bit simpler, only because two terms, internal energy and volume, will be linked to enthalpy of the system and enthalpy of the thermodynamic environment, and for us it will be a restricted thermodynamic environment. So now let us discuss a little bit more in detail these two equations to find some similarities or some different aspects related to physical exergy of the closed system and physical exergy of the open system. So let us assume that closed system, it is just assumption, it is ideal gas. Ideal gas for us will be the example of closed system, and as we can see, for the ideal gas, constant specific heat ratio will be constant, and we will replace equation written in the terms of internal energy, volume, pressure and volume, and temperature and entropy in the form of, so we will replace with the equations for the ideal gas, and we will form equation that will have two parts. One depends only on temperature and second depends on the pressure. This is just for convenience of our analysis. And now we have the following results of the calculation. Vertical axis, it is so-called relative temperature. So running temperature over temperature of the environment. If it is environmental temperature, it will be 1, and all processes below of the environment will be here, and all processes above of the environment, I mean temperature, will be higher than 1. And for the pressure, it also will be relative pressure. If relative pressure is 1, it means that pressure of the environment. Everything which is lower than 1, it is vacuum, and everything which is higher than 1, it is higher pressure than environment. I will not use a special term for that at present. So now we can see that regardless of the combination temperature and pressure, physical exergy is always positive for the system. So minimum value that can be obtained, it is 0, environmental conditions. But after that, does not matter which combinations, temperature and pressure we will consider for the closed thermodynamic system, physical exergy is always positive. This we should remember. So negative is impossible, but we always should keep in mind that it is closed system. I especially emphasize on the fact that it is closed system. Now we're with the physical exergy for open system. Again, we have main equation, so basic equation how to calculate physical exergy for the open system, and we know that exergy, not only physical exergy, it is extensive thermodynamic properties. Then we can rewrite this equation on specific in specific form, for example, based on mass of the system. And again, we can convert this equation that is based on enthalpy and entropy to the temperature and pressure according to the ideal gas, because we assume that stream of matter also will be the ideal gas. So in the previous example, it was ideal gas for closed system, now ideal gas for the open system. So this is very important for us, that properties is the same and only different boundary conditions will affect two results. So let us proceed, and we will have just these two equations are repeat for this slide, model, and now results of calculations for this particular case. So what we did, we had ideal gas. Let us assume that this is in red color ideal gas, and in order to calculate physical exergy, we introduced restricted thermodynamic environment or restricted heat state, where properties ideal gas, it is material stream, and ideal gas also properties of thermodynamic environment, but temperature and pressure for the system and for thermodynamic environment, of course, will be different. This is the meaning of exergy. And now this figure with a higher scale, we will discuss in detail. So again, equation we divided into two parts. One part depends only on temperature, and another part depends only on pressure. And already we can introduce the term thermal exergy and mechanical exergy. So this thermal and mechanical exergy together form the physical exergy. Before we did not mention that, but now we can mention that in general, physical exergy can be discussed as a two-part exergy, thermal exergy and mechanical exergy. Okay, now let us evaluate. Zero exergy, okay, divide by specific heat multiplied to temperature of the environment. This term always constant, that's why we will not consider it. It will be physical exergy. Physical exergy is 0. When relative temperature is 1, temperature of the environment divided by temperature of the environment, it will be 1. And also relative pressure 1. So for this case, physical exergy will be 0. And now we can see if pressure will be continuously higher than environmental pressure, and temperature does not matter, will be higher than environmental temperature or lower than environmental temperature, exergy will be positive. For the environment conditions, physical exergy is equal 0, we already discussed it, but also can be the case that physical exergy is negative. This case is very important for us to understand, and also why it is negative. So we can see that it is not always negative when pressure is below than the environmental pressure. Sometimes contribution of thermal part can be significant, and then negative value of mechanical part will be neglected. or will be vice versa. Thermal part is not will not contribute so much to the physical exergy, but mechanical part will contribute significantly. Then physical exergy will be the negative. So very important conclusion. Physical exergy of the material stream can be positive, can be zero for environmental conditions, and also can be the negative. I always say my students, if physical exergy of the material stream is negative, check your calculations. And check not only calculations, but also conditions. If temperature is higher than environmental temperature and pressure is higher than environmental pressure, then negative value is impossible. Something wrong with calculations. But if temperature can be any higher than environment or lower than environment, but pressure is lower than environmental pressure, then it can be the case that physical exergy is negative. This is very important to remember, because these negative values sometimes will cause problems in our calculations, and later we will discuss how to avoid these negative aspects, that one part of exergy is negative. At present, we only need to remember that it can be the case. So now let us repeat the discussions related to ideal gas. This is our example, ideal gas and restricted thermodynamic environment, where ideal gas is also the working fluid. Let us assume that we need to calculate the physical exergy of some volume of ammonia. So ammonia, it is always very good example, because ammonia does not exist in the environment. So it means that it is some substance that definitely never will be present in the real surrounding, real environment, and can be only discussed for exergy analysis as a substance for restricted thermodynamic environment or restricted dead state. So in order to calculate physical exergy, we need to describe a restricted thermodynamic environment where temperature and pressure will be close to environmental conditions. We already discussed how to select it, but chemical properties of thermodynamic environment, it will be the same ammonia as a working fluid of a system that we need to calculate physical exergy. So now more complex task. Let us assume that within the energy conversion system, 3 working fluids will be involved. We have many examples of such energy conversion systems, and this is not necessarily that these 3 working fluids will be mixed. Maybe it is just 3-stream heat exchanger, and all 3 working fluids will have heat transfer process, but never will be mixed and never will have chemical reaction. So let us assume general case, we have no mixing and no chemical reaction, and for different purposes we use 3 working fluids. In order to simulate the process, in order to conduct energy analysis, to write energy balances or apply entropy balances and calculate entropy generation as irreversibility, we definitely will introduce such a boundary condition. So within boundary condition, 3 working fluids exist. How to calculate now the physical exergy of each of these working fluids, and later proceed with analysis. So each working fluid will be under oven temperature and pressure. So especially 3 colors selected. So yellow working fluid will have oven temperature and pressure, and of course chemical substance should be described. Red working fluid has completely different temperature and pressure, and of course chemical substance. And green working fluid also will have oven temperature, pressure, and description of chemical properties. How to proceed with exergy analysis? In exergy analysis, we need for each working fluid to describe restricted thermodynamic environment. So it means that only for exergy analysis, we will divide these 3 working fluids with another boundary conditions, and that will be restricted thermodynamic environments. For all 3 working fluids, restricted thermodynamic environments will have the same temperature of the environment and the same pressure of the environment. But working fluid will correspond to, so each working fluid will correspond oven working fluid of the restricted environment. And using this example, now I will repeat one definition about properties of the restricted thermodynamic environment that we discussed in the previous lectures, and I already told you that it's very difficult to follow explanation without example. So now let us repeat the definition of restricted thermodynamic environment. Intensive properties of the environment means temperature and pressure assume it to remain constant regardless of how many substances will be involved, but extensive properties means enthalpy and entropy can change as a result of interactions with other systems. So it means that for restricted thermodynamic environment, how many working fluids, so many states zero. This is really very interesting. And all these states zero will have the same temperature and pressure, but each state zero will have own chemical properties, means enthalpy and entropy should be calculated for different working fluids within one system. So I will repeat the rule. I always say my student, this is the golden rule of exergy analysis to calculate physical exergy. How many working fluids are involved, so many states zero should be used to calculate physical exergy. I mean physical exergy of material stream. And now few approaches to calculate physical exergy and to describe physical exergy. This is thermodynamic diagram enthalpy entropy, one of the thermodynamic diagrams proposed by Richard Mollier at the beginning of 20th century, just to help engineers to have to make very fast calculations and simultaneously to have visualization. This diagram, enthalpy entropy, was very popular in that period of time because this diagram, it is the combination of the first law of thermodynamics, energy balance, and the second law of thermodynamics, entropy balance, with possibility to demonstrate entropy generation as irreversibility within the process. And since for physical exergy, the difference in enthalpy is involved and difference in entropy is involved, the first demonstration of physical exergy was exactly using these diagrams. So these diagrams for different working fluids and how people deal with this diagram. So combination temperature at state 1, for example, given conditions, and pressure, it is state 1. Combination the same parameters in the thermodynamic environment, it is state 0, and we can proceed with calculation of equation for physical exergy. We have only one problem, how to deal with the temperature of the environment. And temperature of the environment, it is the line with the angle which corresponds to arctangle alpha, so it is graphical interpretation, change of enthalpy over change of entropy at constant pressure means pressure at environmental conditions. So then graphically it will be environmental line, and we have already calculation that the difference in enthalpy 1 minus enthalpy 0, the difference in entropy 1 minus entropy 0, and T0, it is this line. So it means that physical exergy will be the only vertical distance between state 1 and this state A. That was very long explanation, always in all books in thermodynamics where exergy concept was discussed, and in earlier books or related to exergy. At present, no one will do like that. No one will do these calculations. We have software and no need definitely to describe physical exergy using this diagram. Therefore, it is early approach. We cannot say that it is old approach or wrong. It is not wrong approach. It is just early approach when everything was to the convenience of engineers and diagrams were much easier to work than software, and software actually did not exist in that period of time. So that's why if you will find such approach in the books that authors discuss, just simply how to say, ignore this information because it is early approach, it is old information, and up to now, so no need, already many years up to now, no need to return to this approach and calculate exergy using the diagram. Okay, let us continue also with, how to say, old-fashioned, better to say, It is end of 60s, beginning of 70s. It was also fashion in thermodynamics, in exergy analysis, to develop the diagrams. That vertical axis, it is physical exergy, physical, not total, and horizontal can be different, can be temperature, can be pressure, can be enthalpy, and even the factor T0 multiplied to entropy. So everything is possible. Such diagrams were quite popular, and even some analysis people conducted using these diagrams. But the problem associated with all these diagrams is the following. First of all these diagrams were created only for pure substances. And if we have mixtures, it was no chance to deal with these diagrams. And the most important, it is not only pure substances, under which conditions these diagrams were developed. What was the T0 and what was the P0 for creating such a complex diagrams. So it means that if for some reason, for our analysis that we would like to conduct, T0 will be different that assumed for diagram, and P0 will be different that assumed for the diagram, no one needs this diagram. We need to create a new diagram that will be only valid for particular conditions. Therefore, that was also not useful, and such diagrams can be used only for illustration purposes, but it is also early approach, and this is old-fashioned, and definitely no need to use such a diagrams for really for practical application to calculate physical exergy. And I return to our discussions. Part of that physical exergy can be divided into thermal and mechanical parts, and we can illustrate these parts, for example, using the diagram. If we will use diagram physical exergy enthalpy, we can show under which combinations temperature and pressure, higher environment, lower of than environment, physical exergy of material stream can be positive, can be equal to 0, or can be negative. This is only thermodynamic exercises, only for understanding. As I told you, this diagram is useful, but it is without numbers. Therefore, it is only for illustration purposes, only for academic purposes. But if we really need to calculate this value, we will now discuss how to do it. Up to now, if you observe it properly, physical exergy was divided into thermal and mechanical parts only for the ideal gas model. If we would like to divide physical exergy into thermal and mechanical parts for any state of the working fluids, gas, liquid, saturated vapor, and even in two-phase zone, definitely these simplified equations will not work. Therefore, it was developed engineering methodology, engineering calculations, how divide physical exergy into thermal and mechanical part. This is already the end equation for this model. That was our work in Technische Universität Berlin, Institute for Energy Engineering. We started this work in 2003. In 2005, it was already the first presentation of the results, but finally we published a paper only in 2019, when already all possible cases were covered, and we proved that this equation can be used for all cases. The link to publication Splitting of Physical Exergy Theory and Application will be given in the description of the video, of this video, but I just would like to mention that within this paper we discuss it all cases. Pure substances, mixtures, also splitting of mixtures, working fluid and absorbent for absorption refrigeration machines, and also splitting physical exergy into thermal and mechanical parts for humid air. This is also very important for the exergy analysis of air conditioning system when humidity should be included in evaluation. And at the end of this video, I would like to ask you to give like to this video, because YouTube is ranking quality of interest of video according to the number of likes. And please subscribe to channel and share the link with your colleagues. Our next lecture, lecture 4 in the block exergy, will be dedicated to chemical exergy. Thank you.